Hello, I'm Papia. In this problem, we have an infinite series, -1 to the n divided by n ln of n. We have to figure out if this series converges, and if it does it converge absolutely or conditionally, or it diverges. So, the best way to start is by taking the absolute value of the series and then see if that series converges or not. So that is step 1. So what you do is you take your series but put an absolute value to the terms. If this series converges, then we will know that our original series converges absolutely. So first, let's see what the absolute value will give you. Notice that in the numerator you have -1 to the power n, which means that particular term will oscillate between -1 and +1. But since we put absolute value, that term will always be +1. So you just put +1 on the top. And then the denominator is n ln of n, and n starts from 2 to infinity. So of course, both of those terms will be always positive. So we don't need absolute value next to it. It will be just n times ln of n. So this is the new series that you get by taking the absolute value of the original series. And now we have to check if this series converges or not. Now look at this function. This is an 1 over n ln of n. You see that you can integrate this function, 1 over x ln of x. So let's try integral test. Okay, so in order to apply integral test, we have to first define a function by looking at the terms of this series. The function is just 1 over x natural log of x. Okay, we have to check 3 things, remember. First, is the function positive? Not everywhere, we're only looking from 2 to infinity in that interval. So looking for x greater or equal to 2. Okay, is the function positive? Yes, we just talked about it, right? X and ln of x both will be positive. So f is positive. Second, is the function continuous inside this interval for x greater or equal to 2? Yes, even though things are in the denominator, it will never become 0 for x bigger than 2. So f is continuous. For the third property, we have to figure out if the function is decreasing or not. In order to do that, we can quickly take the derivative of the function and see if it's negative or not. So let's try that. So for third, let's take the derivative of f. Okay, we can do a quotient rule. So remember the quotient rule. You square the denominator. You take this denominator function in the top, take the derivative of 1, which is 0, then minus, keep 1 as it is, take the derivative of the denominator. It's the product of 2 functions, so you need product rule. So x times derivative of natural log of x is 1 over x, plus keep natural log of x as it is, derivative of x is 1. Okay, if you simplify, look, the first term goes away, you have a negative. Inside the bracket you have 1 plus ln of x, and denominator is x ln x, entire thing squared. Now, since the denominator is already something square, it's always positive, numerator for x greater than or equal to 2, ln of x plus 1 is a positive quantity. So with this negative, this will always be negative, which means that the function f, this is the derivative, derivative negative means function is decreasing. So f satisfies all 3 properties, and therefore we can apply integral test. So what does the test say? You have to integrate from 2 to infinity of this function, 1 over x ln of x dx. Okay, notice that one of the limit is infinite, and therefore this is an improper integral, which means you have to use the limit definition. So let's do that. Make it 2 to b. Take the limit as b approaches to infinity, dx over x ln of x. Okay, so we have to use the limit definition, and this is the setup. Before we solve this definite integral, let's think about how to actually find the antiderivative. So let's think, how do we integrate dx over x ln of x? Now, you realize that a simple u substitution will suffice, right? Because we have natural log of x. If you take that as your u, the derivative is 1 over x, which is also present here. So we can rewrite this function as 1 over ln of x times 1 over x dx. So if you do u to be natural log of x, du is 1 over x dx. Okay, so this integral looks like 1 over u and 1 over x dx. This entire thing is du. And hence, the antiderivative is ln of absolute u, but u is ln of x. So this is ln of x plus c. Okay. So we have our antiderivative. Plug it in here, plug in the limits, and then take the limit. Okay. So we have ln of x from 2 to b. So plug in b for x and then plug in 2 for x. When you plug in b, you get ln of b minus ln of 2. Well, let's think about it. When b is approaching to infinity, natural log of b is approaching to infinity because natural log is an increasing function. So if natural log of b is approaching to infinity, natural log of that is also approaching to infinity. So this whole term is approaching to infinity, and the second term is just a constant. So this limit is infinity. Limit infinity means the integral diverges. And if the integral diverges, that means the series that we're working with, the series diverges as well. So what does that tell you? Look, this is not the original series. This is the absolute value of the original series. That diverges. Therefore, the original series does not converge absolutely. That's what we know from it. Okay, so we have to now move forward to our step 2 and see if the original series converges the way it is. If it does, then we will know that it will converge conditionally. All right, let's move on to step 2. So look at your original series, -1 to the n divided by n natural log of n. Let's see, what kind of series is it? Well, it's an alternating series because of this -1 to the n. So we can apply alternating series test. So remember what that test is. Well, first, you have to consider the an. An is the positive part from the series, which is 1 over n ln of n. And we have to check 2 properties. First, what is the limit of this an? What is limit of 1 over n ln of n as n goes to infinity? Well, as n goes to infinity, the denominator goes to infinity, so the whole thing goes to 0. So limit is 0. So that is checked. Second, we have to check if an is decreasing. Well, an is this function, 1 over n ln of n. And we have proved before that 1 over x ln of x decreases. Therefore, 1 over n ln of n also decreases. So, we have this sequence an, limit is 0, and it decreases. Both conditions are checked. This is telling you from alternating series test, the conclusion is series converges. So, the original series converges, but its absolute value series diverges. Therefore, our series converges conditionally. So that's the answer. Thank you.